Hi folks, in this video we're going to focus in on horizontal transformations, in particular what we noticed in the investigation, that they don't necessarily behave in the most intuitive of ways. Okay, so let's start with a function, nice easy function, say f at x equals root x. Okay, now if we look at the function root of x plus 2, okay, so remember what we're doing here is we're not plugging x values into this equation. We're trying to compare it to this more basic square root function. So, a very reasonable conjecture to make here was that is that this function here will just be the function root x moved to the right by 2 units. Okay, that would be reasonable to consider, especially what we saw with vertical translations. But of course, when we actually went through the process, we realized that if I add 2 to the x variable, the effect was indeed the opposite. So instead of moving to the right by 2, it moved to the left by 2. Okay, and then you did this for several functions. You even did it with subtractions, and you realized that this was a pattern. Okay, so we know that that's the pattern. Let's try to figure out why it makes sense algebraically that this should occur. Okay, so let's come back here. So let's say I consider, so again, f at x equals root x, and let me pick that particular point on the function. So say I focus in on 4, 2, so that means when the input is 4 to this function here, the output is 2. So just a reminder, this notation here is just another way of indicating the point. Input of 4, output of 2. Okay, and now we're going to consider y equals f at x plus 2, which I can write explicitly, okay, as square root of x plus 2. Okay, so our goal is to see what is the effect on the parent function root x when I add 2 to the x variable. Okay, so here I want to think of this as a horizontal transformation, so I want to keep that y value constant here. Okay, so I want the y value to remain 2. Okay, and I need to see what x value am I going to need to obtain a y value of 2. Okay, so I know f needs an input of 4 in order to get 2. So that means this input of x plus 2 has to be equal to 4. Okay, but in order to now solve for this value of x needed, okay, because I'm solving an equation, I isolate a variable by performing the opposite operation. So the effect on the original x value of 4 is to subtract 2 from it, okay, not to add 2. So this is why the effect of these horizontal transformations is always the opposite to what we see in the bracket, okay, or what we see in the input of the function. Okay, because when we're determining the actual x value that will give us the required y value, we have to perform the opposite operation. And so that's why x needs to be equal to 2, so that the output, okay, will be equal to 2, because the square root of 2 plus 2, 4, is equal to 2. Okay, so this explains algebraically why this effect should always be opposite. Okay, let's take a look at a subtraction. Just confirm that this will also be the same effect. So instead of x plus 2, we'll try x minus 2. And again, our original conjecture might have been that it would move 2 units to the left, but of course we see that it's going to move 2 units to the right. Okay, so similarly here, okay, if I am keeping the y value constant, okay, I need to figure out which x value will give me an input of, in this case here, 4, because that's the input f requires to give an output of 2. And similarly, we see that in order to solve for x, we need to do the opposite operation. So we have to add 2 units to the original x value. Okay? So in this case here, if we look at it from a transformation perspective, Okay, if I start with a point on f at x, say 4, 2, how will that be transformed to a point on f at x plus 2? Okay, the effect will be to subtract 2 from the x value. So here we have 2, 2. Or here, if we take this point x, y, the effect was to subtract 2 from the x value. Okay, and similarly down here, okay, the point 4, 2 on the parent function got transformed to the point 6, 2. So we added 2 to the x component of the original point. Okay, so this explains why translations actually work in the opposite direction. Okay, but we can make a very similar argument now for stretches. Okay, so say again I have f at x equals root x, and I want to consider square root of 2x. Okay, so again, intuitively we might think that this would create an expansion of the function root x by a factor of 2, meaning we're multiplying all the x components by 2. But again, if I take algebraically first, say f at 2x, okay, and I want, so say again, we start with the point 4, 2, and I want to know what that gets transformed to. So if I want to keep the y value constant, okay, that means that this input here, 2x, needs to be equal to 4. Okay, and similarly, in order to achieve the value for x, I need to perform the opposite operation. So instead of multiplying the x value by 2, I have to divide it by 2. Okay. So in other words, if I take a point on the original function xy, it will get transformed to the point x divided by 2y. Okay, so the opposite effect on the x component as we see in the input of the function, which of course we can confirm by looking at the graph. So again, I start with root x, and I consider the point 4, 2. When I look at the function 2x, we see that by keeping the y component constant, the x component gets divided by 2. Similarly, if we instead take that x value and divide it by 2, okay, the effect should be the opposite. Okay, and we see that it is. Okay, that when we have the square root of x divided by 2, if I keep the y component constant, okay, the x value actually doubles to 8. Okay, so in the end, when we're actually doing these transformations, we don't each time have to justify this behavior. But once we find the pattern, we can now apply it. So whatever transformation, whatever operation you see performed directly on the x variable in the equation, the effect on the x component of your point will always be the opposite. Okay, so for adding 2 to x, the effect on the x component is to subtract it by 2. For multiplying 2 to x, then the effect is to divide by 2. And if we're dividing x by 2, the effect is to multiply. Okay, so in the end, that's the important thing to keep in mind, is whatever you see being applied to the x variable, the effect on the x component is always the opposite. Always the opposite. Okay, that's it for now.